All right. Let's go finish what we started yesterday, ladies and gentlemen. So get logged in, leave your computer at your desk, and then come on back here. You certainly can.
Oh, that's a new one, no? The watermelon? Yeah, sure. The watermelon?
All right, ladies and gentlemen. So we left off yesterday with what element? Sodium. Sodium, ladies and gentlemen. Now, we did calcium, we did magnesium. Were they very reactive? No. So that is a good thing. When we go back to our desk, we are going to write down that the alkaline earth metals are slightly reactive with water. Slightly. They do react, not a lot though. If we were to go over one, can you go up and point out aluminum? Yeah, right next to magnesium. Does aluminum react with water? How do you know? Seriously, how do you know? Anybody ever put water in an aluminum can? Did it explode in your hand? No. Okay? Use aluminum foil, aluminum pans, you put them in the sink, put some water in them, is there a reaction? No. And then again, we have moved over one more family. We went from magnesium, which was slightly reactive, to now aluminum, which is almost non-reactive. So we're seeing that the reactivity decreases for metals as we go to the right. But if we go to the left, it's increasing. And then we can look at up and down. Which one was more reactive, magnesium or calcium? Not a lot more, but it did react more. And we were at this when we left yesterday, ladies and gentlemen. We were at sodium. So let's take it, let's put another chunk of sodium in there just to remind you. Plus, sodium's kind of cool, ladies and gentlemen. Just to remind you of what happened. So, all right, here's our sodium, ladies and gentlemen. Again, when you look at it, it's white. Aren't metals supposed to be shiny? Why isn't it? It oxidized. Even sitting in oil in a container, it is so reactive that it still oxidizes. So we're going to take and we're going to cut a little piece off again, ladies and gentlemen, and we'll go throw it in some water and we'll go see what happens. Okay? We'll see if we can scare Phoebe again today. Phoebe's like, you had to say something. All right, so there it is when we cut it. Now you can see that it's a lot shinier, a lot more silvery. But again, it's going to oxidize. Even sitting here as we're talking, it's going to oxidize and it's going to start becoming duller. All right, let's turn this on. Make sure we got some phenolphthalein in there. Now, the reason for the phenolphthalein, ladies and gentlemen, is phenolphthalein reacts with bases. It turns purple color. So when we put these metals in with water, what we are creating is we are creating a base. We are creating magnesium hydroxide, calcium hydroxide, lithium hydroxide, and those are bases, okay? And bases react with phenolphthalein to turn it pink. So let's see what happens, ladies and gentlemen. I might as well throw some in here right away for the potassium in a second. All right. So, again, you can stay back there if you'd like. If you'd like to get closer, you are welcome to, ladies and gentlemen, and here we go. I don't know. You tell me if it's reactive or not. No, not really. No, not really. Burst into flames, exploded. No, not reactive at all. So now, yes. What are we expecting? More reactive. We are expecting more reactive, ladies and gentlemen. Okay. What? If you'd like to see what happens when you put big chunks, go on YouTube, do sodium metal in water. It'll show you some guy who works at some sort of factory. I believe I forget what factory he works in, but they literally, sodium chunks are one of the byproducts of something they create. He takes them out to his cabin in the woods and he throws them into a lake. and these chunks react. So now, ladies and gentlemen, I used to do these demonstrations in the front of my room. I used to have a blast shield that I would put up, and then I started to use bigger chunks, and that started happening. Okay? And so they have suggested to me that I do it in my fume hood because I've never had to use the fire extinguisher in my room, but I came close with the ceiling tiles one year, ladies and gentlemen. So, and this calcium in here has been here since I've been here, and I've been in the building for 26 years. So this bottle is over 26 years old. Our bottle of magnesium was over 26 years old. This bottle of sodium I recently purchased probably about 5 or 6 years ago. And then I went to purchase potassium because potassium is the next one that we were running out of. So this is all they will let me purchase for potassium. Okay? And read what it says right there, Josie.
Dangerous.
No, above that.
5 small pieces.
5 small pieces. This is $25 worth of potassium in here, ladies and gentlemen. $25. And here's what they now give me for potassium. That's it.
Wait, how many of the pieces have you used? There's 5.
Well, there's one left in here, and there's one there.
Oh, wait.
So anyway, I have to buy some more of this. But they let me buy chunks of sodium that were that big. And that's the biggest piece of potassium I can get, ladies and gentlemen. They have taken all the fun out of chemistry. Okay? It is not my fault. We used to have bigger chunks like this of potassium, and those were fun. Okay? So please, 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 don't be disappointed because this is a lot smaller piece than the last. I'm not putting $10 in there. You guys aren't worth $10. Come on. Ooh, I need a thing of water in there. So let's put this in there. All right, you ready, ladies and gentlemen? You ready? You ready? You ready? Now, what did we get right away that we didn't before? Okay. Yeah, I know. Disappointing as heck, but that's the best I can do for you. But potassium is more reactive, ladies and gentlemen. Now, people always want to go to what element? Francium. First of all, I can't even get rubidium or cesium. They will not let me get it. And francium I can't get because it's $250 million a gram. A gram.
I think this will come in.
Now, it all, apparently you don't know the Green Bay School District very well. The other thing about francium, ladies and gentlemen, is francium is radioactive, and it has a half-life of 22.5 minutes. Which means if you bought a gram of francium at the start of class, after 22.5 minutes, you'd only have a half a gram of francium left. Half of it would decay away into something else. And then after 44 minutes of class, you'd have a quarter gram of francium left. And then after 70 minutes approximately, or 66 minutes, you would be left with 1/8 of 1 gram of francium that you just spent $250 million on, or $2.5 billion, I'm sorry. It's not a good investment, ladies and gentlemen. It's not a good investment, okay? All right, let's go back to our desk. Let's get logged in. Vanna, give me that, please. Thank you very much. All right, let's go. Oh.
Also fun. We'll go home and tell my mom that we did some cool stuff in chemistry today.
All right. So here's where we're at, ladies and gentlemen. We are winding down. Tomorrow, I will find a way to get through the last of the material that we need to get through. So that next week on Monday and Tuesday, we can do practice tests. There are 4 of them in the back of your packet, 7, 8, 9, and 10. You could start doing them. I don't guarantee you could finish them right now because again, we still have a little bit of stuff to go through that we'll get through today and tomorrow. Also, on that yellow sheet, by the time we are done, you had better have something written on there for each one of those things to be able to identify them. Now, obviously, Branium you don't have to worry about because it'll say the most awesome science teacher at East High School. You'll know who that is. Ferkium you will know because that will be the principal of East High School and East High. Some of them I literally just say, orangium is a third period noble gas. All you got to do is take the symbol for orangium and put it where a third period noble gas would go. Now, here's the thing, ladies and gentlemen. When you get a clue like that, you better knock it out of the park. You better for sure get that in the right spot. Because we talked about this before. Every time you get one wrong, you are going to get two wrong. By the way, I didn't tell you yesterday, ladies and gentlemen. I should have told you this. I'm for sale, ladies and gentlemen. Meaning, you can come up and you can buy my knowledge. I will put any element that you want in the correct spot on your test for you.
Jeez.
Test, sorry. I was going to say table. I was going to say test. It came out weird. So if you want me to place the element branium on your test, all you need to do is say, Mr. Brand, place branium on my test. And I will write it exactly where it goes, ladies and gentlemen.
So we can like buy every element.
Sure.
Actually,
At a cost
how much?
of the 2 points you would have gotten for putting it in the correct place.
Oh.
So you want all 50? I'll give them to you, but you get 0 points on the test. Now you may be sitting there going, well, why would I ever do that? Well, there may be a clue where 3 elements, and you know the 3 elements depend on when you place one of them. And you may not be sure. So now the question is it worth buying one of the elements in the spot to know where the other 2 go? Or are you going to take the chance and get all 3 wrong? You want to buy one of them? I'll give it to you. I'll tell you where it goes. Now, what I won't do is look as you go, Mr. Brand, can you give me the answer for number 15 where it belongs? No. If you don't know who the scientist is or what the answer is, I will not place it for you. So if you don't know who the scientist was who was a musician turned scientist, and you're trying to figure out who that is by having me put it there, I will not do that. You need to tell me, please place Newlands on the test where it is, and I will do that for you. Okay? So please keep that in mind. That is an option on your test for you. Again, in the end, you should have it somewhere. Here's the other thing. Maybe you're going to place an element and you're like, I already got something there. But I know this one goes there. So maybe you come up to me and say, well, you place DA, which I accidentally put in the wrong spot. I'll put it in the right spot for you. Okay? I'll put it in the right spot for you. Okay. All right, here we go, ladies and gentlemen. So we got to quickly get through this. All right, which of the following is not a property of a metal? Which one is not a property of a metal? Jaden, which one's not a property of a metal? Brittle. Brittle is the property of a non-metal. Brittle is the opposite of being ductile and malleable. Which of these is the most reactive metal? Which of these is the most reactive metal, ladies and gentlemen? Okay, what family is the most reactive family? So you're looking in the, which one? Thank you. Be careful because I thought that's what you said, but alkali and alkaline, very little difference between. Alkali metals. Where in the alkali metals is it more reactive? So, where is cesium on the periodic table? Alkali metal near the bottom. Where is calcium? An alkaline metal in the middle. Strontium, an alkaline metal further up. And potassium, an alkali metal, but higher up than cesium. So the answer is cesium. Cesium. More reactive non-metal. Nitrogen, oxygen, arsenic, or tellurium. Which one? Oh. Opposite of metals. Metals are more reactive at the bottom. Non-metals are more reactive at the top. So oxygen is your most reactive out of that group. Questions? Which element has the largest ionic radius? Ionic radius. Calcium, argon, gallium, or bromine? Calcium, argon, gallium, or bromine? Which one? Nope, not argon. Argon would actually be the, well, it would be larger than calcium, gallium, and those two. Bromine. Why? No, because remember, ionic radius goes down as you go across the periodic table. But bromine is a what compared to gallium and calcium? And remember, there is a one-time jump in ionic radius. Bromine has 4 energy levels around it. Gallium and potassium will only have 3 as an ion. So they are smaller than bromine. Non-metals are always larger than metals in the same period. Always. Always. All right. Woo. That's wrong. Should be bromine. Sorry. Which of the following elements has the largest ionization energy? Which one has the largest ionization energy? Okay, what element has the highest ionization energy of all? Now, we're not talking about second, third, fourth. We're talking about ionization energy. Which element has the highest ionization energy? Which element is the hardest to get an electron from?
Argon.
Helium.
Oh.
Helium. It's stable. Oh, my God. Get that out of my classroom. Strawberry troll puffs? Oh.
They're good.
Oh. Put it away. I can't even stand the smell of them. Or I'll put them away for you. I got a blue bin over there I can store them in. Okay. Which helium? Highest ionization energy of any element. Why? You can't get an electron away from it because it's stable, and if you were trying to take an electron away from it, it's very close to the nucleus. Which of these is closest to helium? Argon. Fluorine is not an option though up here. Chlorine here, argon here, argon because it's in the same family. Okay, argon because it's in the same family. So argon. Question. All right. Quickly, ladies and gentlemen, take out that periodic table that we gave you.
Which one?
The one that has the trends on it that go up and down or across, family or period. Oh, Steven, here you go. All right. So on here, ladies and gentlemen, on here, group 2 alkaline earth metals, slightly reactive with water. Slightly reactive with water. Alkali earth metals, very reactive with water. All right, questions? Again, it's getting to the point where it would suck to lose this for you. So make sure you know where this is at. Make sure you're able to keep your copy of it. Make sure you don't lose it, ladies and gentlemen. Okay? Make sure you don't lose it. The more you put on there, the worse it will be if you actually end up losing it. All right, ladies and gentlemen. So today we're going to talk about Vesper. Okay? Today we are going to talk about covalent compounds. Okay? So I'm on slide 33 in my notes. Slide 34 is the first slide on Vesper, though. Vesper is an acronym, ladies and gentlemen. Valence shell electron pair repulsion. That's what it stands for. Valence shell electron pair repulsion. This is the reason for singly first, doubly second. Because when you put two electrons in the same region, an S, a PX, a PY, a PZ, one of the 5 Ds, one of the 7 Fs, it is easier to put them alone first and then double them up second. Okay? Double them up second. Now I do want to go back a second to this. Did we talk about, oops, wrong way, carbon yesterday? And what's going on there? No?
We talked about hydrobases of Eddie.
Okay, good. So, there is one valence electron here. Because these are all in the second energy level, I'm not going to do 1s2, 2. We know 1s is filled, right? So this would end 2s1. Here's 2s2. So these electrons pair up here. Why? Because the s's are lower energy than the p's. S is filled first. So we get 2s2, 2p1. But what happened here? Why? Anybody remember what we call it when this happens? We call it a degenerate orbital. This electron right here should be up here. But it doesn't stay there. It gets promoted into here. Even though it's a little bit higher energy, it gets promoted into here. And this is the reason carbon is the basis for life on our planet. Why? Because it can form 4 bonds. 4 bonds. Okay? 4 bonds. Nitrogen can only form 3. Why? Because this is a pair of electrons here. They can't do anything. They're already paired up. But these 3 electrons here can make bonds. They can be shared. Okay? Now remember, we're talking about sharing electrons. Okay? Not gaining or losing, not becoming charged. We're talking about sharing. Okay? If you're going to share with somebody, why would you share with them? You have too many. Well, you're a nice guy. Okay, McDonald's used to play the Monopoly game. The big prize for McDonald's Monopoly game was $1 million. But what pieces did you have to get on the Monopoly board? Anyone? 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 Nope. They used to just give you the pieces on fries and on sodas. And if you collected all the pieces, so for example, the 3 green pieces, if you got them all, you won a free an ATV. If you got all the ones that were red, you got a car. If you got all the ones that were this, you won a Nintendo or an Xbox or something like that. Well, their big prize was $1 million, and you only had to get 2 pieces, Boardwalk and Park Place. Okay? Now, the hard one to get was Boardwalk. So I got Boardwalk, but the contest is running out. Josie's got Park Place. So we could do what? We could share. We could share. Josie and I could put our pieces together. We could go in and we could share the prize, correct? Josie, are you willing to do that?
Let's do it.
Good. 70-30. Right? What do you mean no?
That's not fair.
But you want it or not?
I do.
Okay, so you'll take it?
Sure, why not?
Okay, good. Because if she didn't, Phoebe also had Park Place, and I was going to offer her 70-30 as well. So you want your 50-50, that's fine. I don't need to share with you. Okay, I'll share with Phoebe. Phoebe, would you take 80-20?
It depends.
You get 20% of $1 million, or you get nothing.
Oh, 20%?
Yeah, you get the 20, I get the 80.
Yeah, I want money.
Okay, you want 90-10?
Compared to nothing, you know.
Okay. Point is, I can go back and forth, but I'm willing to share with them and not Pierce. Why am I not willing to share with Pierce? He doesn't have a piece. He's got nothing to give. So the only way these atoms will share electrons is if each one has something to give. What do they give? An electron that is not paired up. An unpaired electron. Because if I give you an unpaired electron and you give me an unpaired electron, we now both have a 1. Okay, another example, ladies and gentlemen. Apparently we need that. So we go to the movies. My wife and I go to the movies, right? And we buy the big old tub of popcorn. Why? Because it's cheaper and it comes with 2 sodas, correct? Okay? So we are going to share the popcorn, which means it's like we both have it, correct? Now, my wife makes me share 50-50 with her. I have to. 50-50. She gets half the popcorn, I get half the popcorn. Problem is, my half is on the bottom, so I got to help get to it first. Okay? So, but we share 50-50. Now, I tried one time sharing with her, but I tried sitting on the other side of the theater. That didn't work very well. Okay? Because I had the popcorn with me on one side of the theater. She was on the other side. It took her a while to realize I sat somewhere else. But still, we couldn't share very good. We had to be near each other to share. And then we both had to have something to give to share. Okay? We had to be willing to split the popcorn. Okay? When you do that, ladies and gentlemen, you both got something to give, you could share. Okay? But again, you've got to be near each other too. Okay? So, carbon could share 4 electrons with any other atoms it wants to. Because they're all alone here. Okay? But nitrogen could only share how many? 3. This is already a pair. So the most it's got to share is 3 other electrons. What about oxygen? 2. What about fluorine? 1. Okay? Fluorine's only got 1, which means fluorine can only make 1 bond. By the way, fluorine could represent any one. Any halogen family member. Now, noble gases can't do this. Why? They're already full. They're not sharing. They're not giving anything up. Okay? All right? They're not sharing. They're not giving anything up. Okay? So, fluorine can only share 1 electron. What other element can only share 1 electron? What other element can only share 1 electron? By the way, if fluorine shares an electron and it gets 1, through sharing, it's like they both have it, right? How many electrons would fluorine have? 8, and it would become stable. What other element has 1 electron, but by sharing that 1 can also become stable? Nope. Lithium has 2 in the first level. No.
Oh.
The other element that could share 1 electron and become stable. Because even if lithium shared that 1, it still needs 8 in the outer shell to fill it up, right?
Another element in origin family.
Well, we said that. All the halogens could do that. I'm thinking of another element on the periodic table besides a halogen. You guys are not my number 1 class. You guys are not at the top.
Hydrogen.
Thank you. Hydrogen. Hydrogen could also do it. Why? Hydrogen has 1 valence electron, but how many does it need to be filled? 2. Hydrogen is just like a halogen in this case, ladies and gentlemen. Hydrogen shares one electron, the halogen shares one electron, they both become stable. Just so we're clear. Anywhere where we use the term hydrogen, we could use halogen. And anywhere where we use halogen, we could use hydrogen. Fair enough? Good. Let's talk VSEPR then. Okay? VSEPR says this, valence shell electron pair repulsion. So these electrons that are not paired up in an S, a P, in D's, and in F's. Well, not D's and F's. Why? Why does it have to be an S or a P? Valence electrons. Why? S and P's are the valence electrons. The D's are one inside. They are not the outermost electrons. We're not going to share D's and F's. We're going to share S's and P's. Good, good, good. It's a model to explain the molecular geometries based on minimizing the repulsion of shared and unshared pairs of electrons. Here's your geometries. You ready, ladies and gentlemen? Good. Okay? Atoms form covalent compounds. They do so by sharing unpaired electrons. They have to have electrons, but they also have to be unpaired. And we showed you what that was a minute ago. We'll show you again. Each covalent bond is a pair of shared electrons between two atoms. Each atom donates one electron. That gives them each a pair that they are sharing. The total pairs is the electrons around the central atom. What is the maximum number of pairs that an atom can have? What? 4! Carbon, 4. That's it. That's the max. Bonding pairs are pairs of shared electrons between two atoms. So there are these things called bonding pairs. So of these 4 total pairs, some of them might be bonding pairs. Some of them might be lone pairs. Those are pairs of electrons around the central atom that do not involve being shared with another atom. We will show you what we mean by these. But these are pretty easy to distinguish. We will show you in a minute. Bonding in lone pairs determines the geometry and the angle of the bonds. Okay, here we go. Total pairs around the central atom describes hybridization. What's a hybrid? I mean, there are these hybrid cars. What's a hybrid car? What? What 2 things? Electric and gas. So it's kind of like having both. It's like having a gas car and an electric car. You run low on electricity, what does your car automatically do? Switch to gasoline. Okay, switches to gasoline. So unlike an electric car where when you run out of juice, you're done, hybrid switches over to gas. It's like both at the same time, right? Okay, well, we have S suborbitals, P suborbitals. How many P's? How many P's? Orbitals, orientations, not electrons. 3. Okay, X, Y, and Z. Well, when 2 atoms share electrons, these orbitals overlap. And we call them hybrid orbitals. They're no longer S's and P's. They're a combination of them because they're sharing electrons with another atom. Hybridization is the overlap of atomic orbitals becoming molecular orbitals. When 2 atoms share electrons, they are no longer S, P, D's, or F sublevels. They are hybrid of S's and P sublevels. We'll explain. All of the compounds are between a representative of the family, carbon family, nitrogen family, oxygen family, boron family. We could even go back to alkaline earth metals. We could even go back to alkaline earth metals because alkaline earth metals are metals, right? What kind of bond should they form? Metals and nonmetals? That's how many? Yeah. What kind of bond? When they make ions. It's not a covalent bond, it's an... If it's made of ions, it's an ionic bond. But here's the thing, ladies and gentlemen. Very few things in chemistry are black and white. And for every rule, there's an exception, and there's no exception to that rule. So even though beryllium is a metal, and even though it makes an ionic bond, some ionic bonds kind of act like covalent bonds. Okay? Okay? Oops, sorry. So, the representative family and either halogen or hydrogen. Why halogen or hydrogen? Because they both need one electron to fill them up. That's it, one electron. Okay? So these are the simplest types of covalent compounds. We're not going to get into ones where they're sharing 2 or 3 electrons, only one. Since the hydrogens and halogens both need 1 electron, they can be shared by filling its outer energy level, and they act the same chemically because they both only need 1 electron and they both only form 1 bond. Questions? So here it is, ladies and gentlemen. Here's the whole shooting match. If you put alkaline earth metals with fluorine, why fluorine? It's a halogen. It's the easiest one to use. You are going to have 2 total pairs. Why? Well, okay, here we go, ladies and gentlemen. This is beryllium. How many electrons around it? How many electrons around beryllium? Come on, how many valence electrons? Somebody give me the correct answer. No, it's not 4. How many? 2. 1, 2. Now, if we bring in a fluorine atom, how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. And if we bring in a second fluorine, again, 7 valence electrons, correct? So if we're going to explain this bond through VSEPR, what has to happen to these 2 electrons? Well, they're not going to leave, though. But they do need to not be in the same s suborbital. We need a degenerate orbital. We need one of these to be promoted so they can be unpaired in the atom. So one of these moves. One of them moves. Actually, they may both move. We don't know for sure. They may both move. But if they move, they do this, ladies and gentlemen. One of them comes over here. One of them comes over here. And now these atoms can share this pair here. And these 2 atoms can share this pair here. What? Yes. But also, what does that do for fluorine? Stabilize it. What's that do for this fluorine? What's that do for beryllium? No, it doesn't stabilize it. How many electrons does it need to be stable? So this is not a stable compound. It's not a stable compound. Okay? Because you don't have 8 around beryllium. But it can happen this way. And if it happens this way, this is what it looks like. What shape is that? A log. Boy, geometry would love you. That's the log shape, Mr. Garai. That's, so what shape? What? Linear. Linear. It is the best explanation we can give for that having that geometry. Okay? It's the best explanation we can give for having that geometry. So, how many total pairs of electrons does beryllium have? How many? 2 total pairs. 2 total pairs, correct? Okay? How many are bonding pairs? 2. How many lone pairs? There are no lone pairs. There's no pair here that isn't attached to something. So we have 2 total pairs. Both of them are bonding. We call that a linear geometry. Why? It's going to be a straight line. So what's the angle on a straight line? What's the angle between here, here, and here? 180. 180. That's where we get this. Now, how many pairs are there? Total pairs. 2. 2 total pairs. 4 electrons, yes. 2 total pairs, right? That means it's sp hybridization. That means it's sp hybridization. Now, if I were you, ladies and gentlemen, this is where I'd be writing this. This is where I would be writing this. And I would be writing this under the alkaline earth metals. That the alkaline earth metals show sp hybridization. The alkaline earth metals show a linear geometry. The alkaline earth metals have an angle of 180 degrees. The alkaline earth metals have 2 total pairs, 2 bonding pairs, and no lone pairs. And they will always have that. Always. Questions? More time needed, or are we good? Anyone need more time? Okay, so now, ladies and gentlemen, now I'm going to get rid of this beryllium, and I'm going to replace it with a true nonmetal. I'm going to replace it with boron. But now boron, the electron should look like this, correct? Yes? No? Maybe so? Should. Right? So how many bonds can boron make? This way, only 1. But you know what we find? We find boron makes 3 bonds. How can boron make 3 bonds if this is the way its electrons are? One has to move. Degenerate orbitals again. Not because we want them, but because they exist. It is the only way we can explain this. So boron takes and moves one of its electrons. Puts it on the other side. Now, again, why does it put it on opposite sides? That's VSEPR. Valence shell electron pair repulsion. If I put this fluorine right here on the bottom and made a 90-degree angle, it would be very close to what? To the other fluorine. Okay? Now think about this. Fluorine has 9 protons, 9 electrons, correct? But when it's sharing, it's like it has how many electrons? 8 on the outside, 2 still in the middle for a total of? What kind of charge will it have? If it has 10 electrons and 9 protons. Come on, come on. No. 10 electrons, 9 protons. What? -1. So if this, and again, it's not really a true full -1. It didn't gain or lose the electrons. It's sharing them, but it's spending time around that fluorine, so it will have kind of a negative charge to it. What will this fluorine have? The same thing. But if I put it down at the bottom here, these two are very what to each other? And close. And what will 2 negatives do if they're close? Repel. This is the geometry that gets them as far away from each other as they can. This is the way this gets as far away from this as they can. That's the key to VSEPR. It wants to get the shape where things get as far away from each other as they can. Okay? Keep that in mind. So now we got boron. I'm going to use hydrogen. Is that okay? Because it's a lot less circles to draw around it. Fair enough? Would be the same if I put in a halogen like fluorine. But I'm going to use hydrogen because you guys are nice and you're not going to make me draw all those circles. So here comes a hydrogen. 1 electron. Here comes a hydrogen. 1 electron. And here comes a hydrogen. 1 electron. Now, what do we notice about every hydrogen here? Put those away, or I will take them from you. No problem. Do you understand? Good. Then give them here and we will solve the problem. The ones that are in your pocket there and those. I guarantee you I won't be eating them. Okay. So, what do we notice about hydrogen here? It's stable. Why? Because it only needs 2. Now, if I were to put fluorine in here, I would have to put 6 more electrons, but it would still be stable. Okay? Still be stable. How many pairs? 3. How many bonding pairs? 3. How many lone pairs? 0. Now, on the last one, we had 2 pairs, right? So we called it an SP because we were using an S and a P sublevel, correct? Here we're using an S and what? 2 P's. This hybridization is SP2. This hybridization is SP2. So now let's take a look, ladies and gentlemen. BF3 would be the compound. I did it with BH3. 3 total pairs. All of them are bonding pairs. Trigonal planar. Trigonal planar means this shape. Why? This is as far away as they can get. This is as far, by the way, what angle is this? Why 120? That's a third of a circle, and a circle is 360. So this has an angle of 120. What is the hybridization? SP2. By the way, there is only one family up here that does SP hybridization. What is it? Alkaline earth metals. Only one family up here does SP2. What is it? Boron. Boron. 3 total pairs, 3 bonding pairs, no lone pairs. Trigonal planar geometry. I'm telling you, that's going to be a question on your test. It's going to be a question on your test. And SP2 hybridization. By the way, only one that has a trigonal planar geometry. Trigonal meaning 3, planar meaning in the same plane, right? Good. Now we need to move. What do we need to move to? We need to move to the carbon family. Now, again, the carbon family, ladies and gentlemen. Carbon is a degenerate orbital. Carbon, 1, 2, 3, 4. 4 electrons waiting to pair up this way, correct? Not carbon like this, because then it could only form how many bonds? 2. This one could only do 2. You cannot pair, you cannot do anything with this pair. This is what we're going to eventually call a lone pair, okay? Haven't gotten there yet, but we're getting there. This could only make 2 bonds, but here's the fact. We know carbon can make 4. The only way that happens is if this electron gets promoted over here. If instead of being in an S, it's in a P, right? 3 individual P's, correct? Okay, now we bring our hydrogens in. What do you notice? What do you notice about every hydrogen? They're all stable. What do you notice about carbon?
It's also stable.
Was boron stable here?
No.
Why not? It's missing two. Well, this compound exists. It's not stable. Why? Boron doesn't have a full valence shell. Still doesn't have a full valence shell. And this is the best it can do. Carbon, however, can do this. Now, carbon, that's stable. That's stable. What's the hybridization here? This was sp. This was sp2. This sp3. We're using all three of the p's and the one s. That's where we get sp3 from. We're using all four of these areas. Okay? All four of these areas. Now, total pairs here around carbon. Bonding pairs. Lone pairs. 0. Okay. Carbon family, degenerate orbital. 4 pairs. 4 bonding pairs, no lone pairs. sp3 hybridization. Here's the shape, ladies and gentlemen. This is a tetrahedral. What does tetra mean?
4.
Okay. One side. 2 sides. 3 sides that are exactly the same, right? No. There's your 4th side that's exactly the same. The one that it's sitting on is the same as all 3 of these. Kind of shaped like a pyramid, whose bottom is the same as each of the sides. That's the tetrahedral. 4 sides that are exactly the same. So what is the angle? 109.5 degrees. What is the hybridization? sp3. sp3. Questions? Okay, now, it is possible that a member of the carbon family might not do this. Might not give a degenerate orbital. If that's the case, you're only going to have 3 pairs around it. Okay? So over here, instead of carbon, let's make this, where's my pen? Got to be in my pocket. It's in my pocket. It's right there. Okay. Instead of carbon, let's make this silicon. And let's say you don't get a degenerate orbital. It can combine with how many hydrogens? It can only combine with 2. Okay? It can only combine with 2. Sorry, all that stuff is in the way at the bottom. My bad. So, how many total pairs here? 3. How many bonding pairs? 2. This is now what we call a lone pair. This is a pair of electrons. Now, here you only had 2 bonding pairs, correct? What shape was this? Linear. This is not linear. This is not linear. And the reason for it is because of these 2 electrons right here. That is an area of negative charge. 2 electrons are there. So because of that, it causes these to, instead of being in a straight line, to be what we call bent. Bent. Okay? So that's where I get the information from that is here. Now, I've updated your test. I will tell you this, I do not talk about these at all on your test. But this would be sp2 hybridization with a bent geometry. We don't talk about that on your test, just so you know. Okay? Now let's go to nitrogen. Okay? Nitrogen. Nitrogen looks like this, which means how many bonds can nitrogen make? 3. It can't do anything with these. These are a lone pair. It can't do anything with these, but these can be shared. So hydrogen can make 3 bonds. It can combine with 3 hydrogens. Here, here, here. What do you notice about every hydrogen? What do you notice about nitrogen? It's also stable. How many total pairs around nitrogen? How many total pairs around nitrogen? How many total pairs around nitrogen? 4. How many of them are bonding though? 3. And then there is a lone pair. Then there is a lone pair. Okay? Now, we had another one where we had 3 bonding pairs. That was this one, correct? A trigonal planar shape, right? 3 sides all the same in a plane, correct? Well, this lone pair here screws that up. This lone pair here repels each one of these, makes them move away, and it changes our geometry. Instead of a trigonal planar, we get a trigonal pyramidal. We get this. This represents that lone pair of electrons. And what this is doing is literally pushing these 3 atoms away from it. Which means this is no longer flat. So this is a trigonal pyramidal. Trigonal meaning what? 3. Pyramid meaning pyramid shape. But it's not a tetrahedral. Why? Because it doesn't have that top. So not all 4 sides are the same. This side, and this side are the same, but they don't match the bottom. So that's where we get the term trigonal pyramidal. It's a pyramid, but only with 3 sides the same, unlike this one, which had all 4. Questions? Okay. Woohoo! You're going to make it, ladies and gentlemen. Now we go to the oxygen family. Now we go to the oxygen family, ladies and gentlemen. Okay. Now, oxygen. Six electrons around it, correct? Anything in the family would have 6 electrons around it. Okay, so these are family trends. Bring in a hydrogen. Boom. Bring in another hydrogen. Boom. Everything stable? Yes. Everything. Hydrogens are stable. Oxygen is stable, right? How many total pairs around oxygen? 4. But now how many bonding?
2.
Only 2. Which means how many lone pairs?
2.
The bonding and lone pairs need to be equal to the total pairs. 2 and 2, 3 and 1, 4 and 0, got to be equal to the total pairs. Okay? So now oxygen gets this shape. Here are those 2 lone pairs. Here are the 2 hydrogens. This is called a bent geometry. It's bent. It's not linear. Without these pairs up here, this would be a straight line. But these pairs are pushing these away. Okay? Pushing these away, ladies and gentlemen. So therefore, oxygen family, still 4 total pairs. 2 of them bonding, 2 of them lone. Bent geometry. 109.5 is the angle. I don't think I asked you about angles on the test. Don't panic. sp3 hybridization. Why? Total pairs, how many? What hybridization? Come on. How many total pairs? What's the hybridization? How many total pairs? What's the hybridization? Total pairs determine hybridization. How many of the S's, how many of the P's are you using? Okay? When you're only using 3, it's SP2. If you're only using 2, it's SP. If you're using all 4, it's SP3. Okay? One more to go, ladies and gentlemen. One more to go. I'm going to go back to using fluorine. We're going to put it with another fluorine. I'm changing the color just so we can keep the electrons straight. These are shared. Which fluorine do we want to describe? Which one is the central atom, the red or the blue? Doesn't matter. It really doesn't matter. But let's pick the red. How many total pairs around the red one? How many would there be around the blue? 4. Doesn't matter. How many bonding pairs around the red one? How many bonding pairs around the blue? 1. How many lone pairs around the red? How many lone pairs around the blue? Doesn't matter which one you pick. I don't care. Doesn't matter. What would be the hybridization? SP3, because you're still using 4 pairs, correct? Now, how many atoms do you have here? What's the geometry? Yeah. It's linear. Here it is. Here it is. These 3 are still pushing away from this, but because there's only 2 points here, the only thing you can have is a line. Linear. Linear. Questions, ladies and gentlemen? Now, here is the key, ladies and gentlemen. You need to get this stuff onto here for yourself. The main thing, the 2 main things, geometry and hybridization. Geometry and hybridization. Okay? It's not that these other things aren't important, but those are the 2 most important. Now, what family is not in here? And alkali earth metals are too reactive to even think about sharing electrons. They're going to gain or lose it. They're going to form an ionic bond. Okay? Alkaline, we could kind of fudge it and say, if they did form kind of a covalent compound, here's the best explanation we could give you for it. Questions? Good. That was it. We were done. Get everything copied onto your periodic table, ladies and gentlemen. If you have questions, if there's worksheets that you have questions on, if you basically want to know how the world works, please let me know and I will tell you. No. Nope. Nope. You said nope? Oh, okay. I hate hiccups. They're annoying. They're terrible. They're kind of like kids. Anyway, just kidding. I love my children, ladies and gentlemen. 4. I do. The only ones I don't have on there are probably 7, 8, 9. But I think, let me double check. Classwork. Unit 8. Oh, I guess I never put out the... I will get the answer keys out there by the end of the day today. Sorry. I will get the answer keys out there.